and see what's going on. Yeah, energy drink might help after several hours. So this is the schedule, and let's see. It or started when we were thinking about Project ForceWorks, and Willem already talked a little bit about that, where we collect force ideas and discuss them. And we were discussing how linear regression might look like, and if there's a simple force solution. And I remembered that I learned programming using the Texas Instruments 57 calculator back in school, actually. And it came with this manual. And the manual, I found a PDF scan on archive.org, was exceptionally well done because it taught me how to do programming. Actually, the programming of this calculator, it has 50 program steps and 8 registers. And you had to think about what keystrokes you would do to do some calculations and so on. And it has labels and subroutine calls and gotos. So everything that you would expect from an assembly language is already there. And so I learned assembly programming using this. So of course, TI-57 is assembly language, but still. The book had a chapter on linear regression, actually. So it not only showed how to do simple things, but also showed how you come from an idea to an actual program. They use railroad diagrams to show how the control transfer takes place, and so on and so on. And there was also a chapter on linear regression. And so I just show this one because this shows in the end how to use it. So you have X and Y pairs that you want to collect. These are the coordinates of points. And you want to find the best fitting line, the regression line that goes there. So you enter the data points, and then you could invoke some of the subroutines. And this is not reverse Polish. Maybe things would have turned even different if I had a Hewlett-Packard calculator in the first place. But anyway, you can learn force even if you have a Texas Instruments infix type calculator. Anyway, it calculates different aspects of this. And I remembered when we had the recent discussion, there was this chapter on linear regression. So I took this data for my test of the force program later on. So we put this aside and start with the talk. I will talk a little bit about what linear regression is in the first place. And as you've seen on the previous slide, it deals with non-integer numbers. So the slope and correlation coefficient and so on, these were all non-integer numbers. And you could use a force floating point package, of course, and use that. But I thought, well, many force systems do not have that, so maybe have a look at fixed point arithmetic. And so we will look a little bit into fixed point arithmetic and how to realize this in one screen, on one slide. Then we had some discussion today about libraries. So I will present my take on that very shortly, need and unit, and how to do modular programming with this. And then we come back to linear regression using fixed point arithmetic. And I show you my implementation, which is a straightforward transliteration of the formulas into force programs. And we have a look at the live thing. And then, of course, there's some time for your questions and my answers about that. So, yeah, let's see. I keep this very easy and very simple. So you get a set of dots, X values and Y values, the blue crosses in the graphics below. And the task is to find the line that best fits these dots. So, and what you typically use some kind of measure how far off the crosses are from a given line by squaring the distance that you have. And you try to minimize the error that you do and find the one that fits best. Of course, it could be that the points are in a way that you can't find a very good straight line to fit it. So you want to have some kind of measure of how to do it. Yeah. And yeah, you can describe a straight line with a slope, what direction it points to, and the intercept where it crosses the y-axis. And then, of course, if you have some number, then you can see what does the line actually predict in that case. So if you go for 9, then you end up with 30 something, although there is no blue cross, no dot that is there, some kind of interpolation that you are doing. Okay, so that's the idea. And let's see, next slide. Here we go. If we want to calculate the slope x, the slope m, and the intercept b, then we can use these formulas. You can look them up in a textbook or ask your favorite math artificial intelligence to show it to you. And what we see is we have sums of the product of x and y, sums of the x's, sum of the y's, x squares, and also, yeah, well, these sums again, and the m that you calculate can be used to actually then calculate the intercept. So what you can do is you can incrementally, even if the points come in one after the other, you can build up these sums, and then at any time you can go ahead and calculate slope and intercept of the regression line. Okay. So we keep this for a moment. If we look at force systems, then we see that some force systems, of course, support floating point arithmetic, but there are some or many systems that by design only support integer arithmetic. And we had this discussion also, and especially for embedded systems, you want to maybe just have integer arithmetic if your CPU doesn't support a floating point with a floating point unit. But still, as we see with the linear regression, we want to deal with non-integer numbers. Yeah? And the idea of fixed point arithmetic is, well, we could scale the integers by a factor, and it could be a power of 2, a power of 10. So they represent the values in units of a tenth, a hundredth, a thousandth, a 10,000th or so. If we choose a 10,000 for decimal places, then 3.1415 is represented as 31,415. And this is a comma because the decimal point in German is a comma. So needs to be cleaned up. Okay. And what you need then to do is to change the arithmetic to take care of the scaling. And obviously, if the point is always at the same place, then adding and subtracting is as ordinary. You just do it. But with scaling, with multiplication, you have to take care of the scaling. And with the division, you have to take care of scaling because of the scaling factor that is actually in there several times. So you have to compensate this. So yeah, we go ahead and have a look at how a fixed point arithmetic package would look like. So if you go from a single integer to a scaled number, a fixed point number, then you multiply it by the scale. Yeah, so a 1 becomes 10,000. Yeah, and likewise, if you want to go from a fixed point number to the integer number that is its integer part, then you divide by scale. And you can define an x dot. So I use the prefix x for fixed point arithmetic. X dot takes a fixed point number, and then very similar to the traditional implementation of dot, goes ahead and displays and creates the digit representation of the number, having the decimal dot at the right place. Yeah, so places is a constant that tells us how many places there should be. Okay, that's more or less what it is. We want to do this at decimal all the time, so it saves and restores base in between. As I said before, plus and minus are like before, and x time fixed point arithmetic multiplication has to take care of the scaling factor, because if you multiply two scaled numbers, then the scaling factor is in there twice, but in the result it should be there only one. Luckily, we have these nice operators that Chuck Moore invented, times slash, that can do this. It multiplies x1 by x2 and divides by scale, exactly what we want here. And for x divide, we just flip x2 and scale to do this. So with these definitions, what we can do is we could 22 over 7, we can calculate that, which is a good approximation of pi. So we convert 22 to a fixed point number, 7 to a fixed point number. We divide them, so we get 22 over 7. And then we print it, and it really gets 3.14. And then the rest is rounding errors. Yeah, but anyway, or approximation errors of this fraction. So if we want to use fixed point, we can encapsulate this in a unit. So we write unit fixed point, and this should be external. And then all the words that should be visible by this unit will be placed between external and end unit. And so these are the words that you provide by this package, by this unit. And if you, at some point in some other part of the program, you want to be sure that the fixed point words are present, you just say need fixed point, and then the system takes care of identifying where the appropriate library code is and loads it into the system. Which brings us to need and unit. So I already explained a little bit about that. So with need, you make sure that a word actually exists in the dictionary, and if it's the name of a unit, then this unit will be loaded and exist afterwards in the dictionary. And the syntax for unit is unit, you give it a name. We have some internal definitions that are not visible outside for outside library, for outside programs. So internal library definitions, you come to external, then you expose and define words that are supposed to be used by other parts of the program, and you end with end unit. Very easy to implement, very easy to use. And we ported need to several systems. I will show it in GForce, but you've seen it already today in NoForth. And there are other systems that have similar capabilities, of course. But the idea here is to get some common ground with need. And you can use need and unit very well together, as we see here, but you can also use them independently if you want to. So that's orthogonal. So let's come back to linear regression. We learned that we need these sums, x times y summed up, the x is summed up, the y summed up, the x squares summed up to do this. And so what we say is we need fixed point, and we define the unit linear regression. And if you have to happen to have a FORCE20 somewhat a standard system, you have the word plus field, but on other systems it's not yet implemented. So you just say, okay, I want to define a record with different fields. I need the word plus field. So you just say need plus field, and then you're on safe ground. And you define a record structure that is called regress. Number regress is the number of memory that needs to be allocated for these. And at offset 0, you have the field underscore n, and then some x, some y, some xx, some yy for some other calculations, and some xy. So these are the sums that we get from the formula. Right. And then what we need to do is we need, if we assume we already have the sums set up, which we do down here, or we have the word regression that returns a regression identifier, which is actually a memory location in the dictionary. It allocates above enough memory for the sums to be stored, and then sets them all to 0. And what we want is to add a new pair, assuming x and y pair is assuming that these are fixed point numbers. We add 1 to n, and then we add x1, which is x, to the sum of x, y to sum of y. We multiply the x to sum up the square of x and the square of y. And then we multiply x and y to get the xy, some xy address. X plus store, I don't know, we go back. Did I actually do? I didn't capture this in the, yeah. But you can assume how it works. It reads the value, it x pluses the value on the stack and then stores back the appropriate thing. So yeah, add pair actually updates the regression by 1 pair. And if you want to supply integers and not fixed point numbers, then you convert them to fixed point numbers first. And that's maybe what we want here. And then if you did this, then you can do the appropriate calculation that we saw earlier. Yeah, you extract the appropriate sums, do the fraction, and so on. And here's something where I say, well, it was not difficult in this case, but of course the formula is mathematical, more infix, and we have to convert it to postfix. For 2 formulas, I will actually do that, but if it happens that we would have more infix formulas and it becomes tedious, I would extend force so that it can take infix formulas and create this code while compiling. Anyway, this is how the slope is calculated using these sums. And actually, this is the fraction that we saw earlier. And the intercept is calculated like this. It makes use of the slope and also has a fraction. And if we want to if we know slope and intercept, we want to predict a value y for a given value x. Yeah, then we say x in a specific regression, and we get the value y, and we do this by multiplying x by the slope and adding the intercept. Well, that's middle school math. Right. And how do we use this? Yeah, we create a regression, and that's maybe our sales figures. Yeah, and then we add the appropriate things to it. And remember the printout from the manual in the TI 57 handbook. It's just these numbers. Yeah, so you add them to the sales regression. And then you can figure out what the slope for the regression line is and what the intercept of the regression line is. And then you can take a 9 and predict whatever the value that the y value that is associated to 9 is. Right. So let's see. That's what is that? This way. Now we come to a demo. which is nothing really interactive, but it can be. So we just start GForce so that it has the need capability, and then I just say need linear regression. And linear regression, if we look at it, yeah, it does a couple of needs in there. It needs fixed point, and it needs plus field, and it also needs unit, because GForce currently doesn't support units, so it has to be loaded. We do it like this, and it does all the loading of the library modules on its own. And then it actually, if we go down there, it actually runs what we had here on the slide before. It adds all the points, it calculates the slope and the intercept, and then also the correlation coefficient and the determination of coefficient, and then does some other calculation. Yeah, so that is what we get here. We get these things, and let's see when we go here and to this slide. Yeah, then we see, aha, the calculator example said something like 2.6837. Ah, great. Yeah, the intercept 6.13745. Okay, with 4 decimal places and fixed point arithmetic, not bad. And then the determination 0.04 hidden here. And the correlation coefficient 0.86. The closer to 1, the better the correlation is. The closer to 0, the worse the fitting of the line actually is. And then we have the prediction for 9, that is 30.29, and the reverse prediction, what is the x value for the y value, 75. 25, and again hidden 6.5. So that works out fine. Yeah. Okay, so that's great. So far, so much for the demo, and you now can interactively calculate with fixed point numbers and so on, and write your program. So that's all easy. Right, so which brings us to the end, and some words of precaution. Of course, if you scale by 10,000, then you have to be very careful of overflows, of course, because you use a couple of bits of your number representation for the fractional part. And this limits the integer part of the numbers. And if you calculate, and we've seen we have sums of squares and things like this, then it's very likely you run into an overflow, especially if you have a system that only has 16-bit integer arithmetic. Then it wouldn't probably work. It works fine with 32-bit arithmetic, and GForce that we saw is 64-bit arithmetic, and you don't have any issues there because the numbers are very large indeed. So if you look at -1, yeah, then it's actually a very huge number considered being unsigned. So you're not very likely, if you cut off 4 places for the fractional part, then you still have a huge number range. But not in the 32-bit case, you have to already be careful. And in the 16-bit case, if you cut off 5, you can't really. Yeah, so you have to use just maybe 2 decimal places or so. Okay, yeah, so that's what I would have liked to talk about, linear regression. In principle, we looked at fixed point arithmetic, my take on libraries in Force, and we saw the implementation more or less, and we saw that it actually matches what was in the 45 years old Texas Instruments manual, and that's it. So I'm open for your questions.
Ulrich.
Yeah.
It's not a question, it's my system only work with fixed point,
Yeah.
and use for all. One thing for add, if you use a power of 2 for scale, you can remove the division of money of this operation and be more fast.
Yeah, sure. I thought about this the other day, and my idea here was actually, we can make the idea as simple as possible. Yeah, and if you use a power of 2 scaling factor, then the printout would be slightly more difficult because you can't just take that number of places. Anyway, and of course, then you don't need to multiply and divide. You can just use shifts to do the appropriate operations. Yeah. And of course, for some professional implementation, you would go for a power of 2, especially that multiplying by powers of 10 and dividing will bring in rounding errors. Yeah, because not all the numbers are represented appropriately. So you have to be careful there. And with shifting, power of 2 doesn't lose you any accuracy. So that's probably good. Yeah, thank you for the hint.
I have implemented all the transcendental function in fixed point, and printing and parsing numbers too is open source. If
Okay.
any
Yeah.
can.
I will have a look. Sure.
And I have the graphic program for see the linear regression. If you like, I show you, but it's your it's your space.
Yeah, you can just give me a hint and I will have a look afterwards. Yeah.
Okay.
Just maybe you just send the link or so. Great.
I have used the fixed point for Euler problems that involve chances, and then you have no problem with scaling because you have always an extra factor 10 or 100, and you need not to worry. But in general, you have the problem that the X and Y scaling is not necessarily compatible. For Y, you could have numbers in the thousands, and for the X split. Have you any idea to solve that?
Yeah, the issue only arises with the sum where you have to sum X multiplied with Y. Otherwise, you could just scale X and Y's in a different way. And for X and you have the sum where you sum up the X times Y values. Yeah, I think you would harmonize them at that point, and maybe you lose some accuracy in there. So yeah, we need to figure out this. So, but in principle, I see not a major difficulty in doing so. In the code that I presented, this is the place where you have to put in some thoughts. Yeah, but you're right. The scaling of X and Y values could be different. And the ranges, of course. I mean, floating point is mainly not only for dealing with non-integers, but also having large ranges of numbers, very small ones and very large ones, and being able to represent them all. Yeah.
And then your regression, you have normally numbers that are of the same comparative magnitude, of course.
Yeah.
is not a problem.